Welcome to yet another static electricity video. This time we're going to talk about what affects the force that two charged objects have between them. So if I have two charged objects, they're going to feel an attraction to each other if they have opposite charges, or they'll feel a repel from each other if they have the same charge. But what is going to affect how big that attraction or repulsion is? So if I have these two charged objects, and we use the symbol Q to signify a charge, so Q means charge. If I've got these two charged objects, what could I do to increase the size of the force between them? Now in this case, they're the same. Let's say I've got a positive and a positive. So they're going to be repelling each other. What are the things that I could change to make that repelling force bigger? Think about it for a minute. What could you do? What could you do? What could you do? Well, a lot of times people come up with the two things that actually do matter, and you may have come up with both of them too. If you only came up with one, great. So you might have said the distance between them. Distance between the charges. And yeah, definitely that affects the size of the force. If I bring these two closer together, that means they're going to have a stronger repelling force. So closer is a stronger force. And the other thing, it might be a little harder because the way I kind of set it up, the way it's hard to think about how you would do this, but you can, let me just not say increase, but you can change the amount of charge on the object. Change amount of charge. And this one, you can probably imagine, so if the charge goes up, if the amount of charge goes up, that gives you a stronger force. Okay, so those are the two pieces that affect the size of the force between two charged objects. And let's do this one first. Let's deal with the charge first. If I have a plus Q and a plus Q, and I'm not going to worry about numbers, I'm just going to think about it in terms of kind of relationships. Let's say I've got these two charges at a distance of r from each other. And that produces a force F. You can make up numbers if you want. You could say, you know, this is 3 and this is 3, that's 5, and, you know, that'll produce whatever that is. What do you think would happen if now I say this is a plus 3Q at a distance r from plus Q? So I'm going to triple the amount of charge on this charge. So now it has 3 times as much charge on it. How's the force going to behave? Well, more charge means a stronger force, and it goes up directly. This means 3 times the force. If we triple the charge, triple the force. It also means that if I have plus 3Q at a distance of r from, let's go plus 2Q, what would we have there? Well, I triple the force because of that 3Q. I double the force because of that. It's going to be 3 times 2, so it's going to be 6 times as big. And so with the amount of charge, it's just a direct linear relationship. Triple it, the force triples. Double it, the force doubles. And then you can just combine them to say 3 times 2 gives you 6. So that's the first step. The second step is a little bit harder to think about. And to think about it, I want you to imagine a small balloon. I'm going to draw a 1 centimeter square on that balloon. All right. Now, let's say the balloon is 10 centimeters across. And this is 1 centimeter by 1 centimeter. Ooh, this is sloppy. So if I have a balloon that's 10 centimeters across, and I draw with a marker on it, 1 centimeter by 1 centimeter square. Now, what's going to happen if I double the size of that balloon? So now it's 20 centimeters across. If I double the size of the balloon, what do you think is going to happen to the size of this square? Double the size of the balloon, 1 centimeter is going to become what? Bigger. You can imagine it's going to be bigger. Bigger by how much? If you guess that it's going to be bigger by a factor of 2, you're right. So something that was 1 centimeter across is now 2 centimeters across. And it's 2 centimeters here as well. And so we've got this direct relationship. Yep, if I double the size, it's going to be doubling. The 1 centimeter across goes to 2 centimeters across. But here's where we get to the interesting part. I want you to think about the area here. That area is 1 times 1, so it's 1 square centimeter. What's the area here? Still a square, so it's just side by side, but now it's 2 times 2. It's 4 square centimeters. So we doubled the distance, doubled the size of the balloon, but that area went up by 2 squared. If we went to 30 centimeters, so if we had to, we're not to scale, let's say not to scale by a lot. So if we have a balloon and we make it 30 centimeters across now, then it would be 3 centimeters by 3 centimeters, and that would give us an area of 9. So 9 square centimeters for that balloon. So this is called an inverse square law. This is called an inverse square law. And it's that squared piece that is the sneaky thing. And it relates to the size of the force between charges with what I just erased, which is that closer is stronger, farther away is weaker. But it is not a direct relationship like it is here. If I have plus q at a distance of r from a plus q, I said that gives me just my standard force F that I'm comparing against. If I have plus q now at 2r from a plus q, so same amount of charge now, but I'm doubling the distance, well, you can probably imagine that the force is going to be smaller because we're farther apart, weaker force, but it's not half as strong. This is where we have to go by the squared. We end up with 1 over 2 squared times the force, which is a quarter. If we triple that distance, plus q at 3r, so on and so on, plus q, what happens is it's 1 over 3 squared times the force, which is 1 over 9. And so this is the inverse square law. It's inverse because we have to go over. As the distance gets bigger, the force gets smaller. They're inverses of each other. One gets bigger, one gets smaller. And then it's inverse square because we have to square this factor. So if we change the distance by a factor of 3, the force changes by a factor of 3 squared. And so we can go the other way too. And let's, I think I had a number. Let's say we have a plus 3 charge, and it is 40 centimeters away from a plus 4 charge. And I'm going to say this gives me a force of F. New thing. What if I have the plus 3 and I move it down to 20 centimeters? So now we're twice as close. What's that going to do to the force? Let's see. You know what? I'm going to redraw it so that's a little more to scale because it's a little bit easier, I think, to make sense of it. So now the plus 4 is here, and we're 20 centimeters. What's going to happen to my force? So I'm much closer. If I'm closer, I should have a bigger force. And my distance changed by a factor of 2. So I went down by half, a factor of 2. That means my force is changing by a factor of 2 squared. But it's not going to be 1/4 because I know it has to go bigger. So in this case, it goes bigger by a factor of 2 squared. The force is 4 times bigger. So if I have 2 charged objects and they have a certain amount of force, if I put them twice as close, I guess you want to call it. It's 2 squared, it's 4 times the force between them. If I triple the distance between them, it's 1/9, 1/3 squared, the distance. And so this is the inverse square piece of the force between 2 charged objects. And if you connect all these pieces up, the amount of charge and this distance piece, you get an equation which is called Coulomb's law. And Coulomb's law is the force between 2 charged objects. And it's given a K, which is just a constant, it's a constant number, times charge 1 times charge 2 over the distance between them squared. Coulomb's law. And then I like to put absolute values around it because Coulomb's law only tells us the size of the force between 2 charged objects. It doesn't tell us anything about direction. To figure out the direction, we have to look at the physical situation and say, these are the same type of charge, they repel each other. And so this is Coulomb's law. But what I want you to just think about conceptually is the bigger the charge, the bigger the force, and that's a direct relationship. If we double Q2, we double F. If we double the distance, that goes up, that means the force goes down by a factor of 1/2 squared. So inverse square. Those are the 2 pieces of Coulomb's law that I would like you to keep track of. All right, I think we've covered everything. Good job.